I want to have every connected component of K to contain at least two roots to be, of course, otherwise I could just take very small arcs around every root, and that has arbitrarily small capacity. And now it is more restrictive to have such an incidence, but still it's possible occasionally that the capacity of K is less than 1, and P is monic and has all its roots in K. The fibers over K, this is Fekete's theorem, are finite. There are only finitely many such P. But for instance, if we take what I am calling the hedgehog, maybe not the most aptest name, to be the union of straight line segments joining the origin to the roots of a polynomial. If we take, for instance, these Zellmer trinomials, this certainly has capacity smaller than 1. And nonetheless, we can say something under more some conditions. But I will start with some typical statements and results that we can prove in this by the method that I will introduce. The first is an explicit form of the conjecture of Schintel-Zassenhaus. That was the case of the Lamer problem, where the Galois orbit of algebraic integers was maximally equalized around the unit circle. The result is that unless the Galois orbit consists of roots of unity, it will contain at least one element outside of this explicit disk. Its radius is slightly larger than 1 plus log 2 over 4n. So it is of the up to the constant of the sharp of the best possible shape. And we can say more in the atorial situation that no roots hit the unit circle, then we can improve the constant by an additional square. And I also want to point to the, I think this illuminates the nature of this method, that the method uses an input from 2 primes, with 2 and infinity for these basic cases. And it can work also just as well over the relatively over totally two-adic fields with the same input, and also over abelian fields, cyclotomic fields, or even their composita. But let me just take L to be one of those, let's say QAB, or the maximal totally two-adic field. And this is a certain Galois infinite extension of Q, and relatively over it, the relative Schintel-Zassenhaus statement, this was new to me, I did not expect this at the outset, looks as follows. We take all complex embeddings of this infinite field. And of course, there are infinitely many, but only finitely many of them are relevant. We have to take the coefficients of the minimal polynomial of alpha. And then if we average over all of these embeddings, these houses, or rather max of log plus of the conjugates over L, on average are again greater than or equal to log 2 over 8n, where now n is the relative degree over L. This may be not so interesting at the outset, but I want to point to, I think it illuminates what is going on. And also, now we can use input from a prime P, any prime P. The bound looks modifies by a factor P squared in the denominator. And that raises in particular the question if Lamer's conjecture on the height could possibly hold not over Q, but even over totally p-adic fields. I think this was new, that there was Amoroso and Zanies Dobrovolsky bound over Q up, but over Q totally p-adic. This minus 2 exponent is a particular case of the SZ theorem. We get, it is sharp for the house, but for the height, we lose one additional exponent. But Actually, here is some
question.
Yes. Should I go back to the previous slide? Yes.
Is totally p-adic, does that mean that P is the only ramified prime?
Oh no, it means that this decomposes totally, splits completely. That P is unramified and decomposes into degree 1 primes completely.
Oh, I don't know what it means. Totally p-adic field.
Totally, yeah, the p-adic analog of totally real. Just that if you take, maybe if you see my blackboard on the, I'm not.
Yeah, I can see it.
Okay, so if you just take the number field, tensor it with QP over Z over Q, then this is a product, isomorphic the product of copies of.
Oh, it simply means that P splits completely. Okay.
That's what it means. Yeah, it splits completely.
Oh, okay.
And if we take the compositum inside Q bar, inside the inside Q bar, then it's a Galois extension of infinity.
For the record, could you state the Lehmer conjecture? Just.
Oh, of course. So on the board. So the Lehmer conjecture in this notation, I have. All right. So I should explain a bit of notation on the bottom of the slides. I have the height. By the height of alpha. Please tell me if this is not visible. But the height of alpha is the logarithmic absolute Weyl height, which means I take the logarithmic Mahler measure on as the numerator. This is like arithmetic degree, and divide it by the degree of alpha, usual slope quotient of these two degrees. And so in these terms, the Lehmer conjecture, which states that the Mahler measure is bounded away from 1 if alpha is not, if the polynomial is not cyclotomic, is equivalent to just height of alpha greater than a constant divided by degree of alpha.
Yep, thank you.
So, right, and now you see here, this has Q replaced by an infinite field, Q totally p-adic, but the exponent is worse, -2. And here it is the best possible, -1. What is lost is that, right, the result only estimates the maximum of the roots rather than averages, rather than Mahler measure. But there is something new which is not in my paper on this subject, which is, I was asking myself, this was a p-adic application over totally p-adic numbers, and it was not at all obvious what an Archimedean analog might be of this kind of result. And I realized that we can say something, I'll explain this. Today, we can say something about Weyl numbers on the Galois orbit of algebraic integers on a circle of radius square root q for the interesting cases where q is a power of a prime, so we take a finite field H2. And we look at degree 2g such numbers. They have to be, of course, symmetric under the real axis, and otherwise be quite arbitrary. But the problem here will be to take two such tuples. So we take the same finite field, and we look at like pairs of abelian varieties, both of dimension g. Without common isogeny factors. What this means is that the Frobenius eigenvalues alpha I and beta I are going to be disjoint. And I would suppose that we can pair up the roots around the circle maybe not in this order, maybe beta I will come up before alpha I, so here is a no shadowing a gap statement about such pairs of alphas and betas. Just for simplicity for the proof I will present in a moment, suppose that Q is bigger than 4. We can accommodate for that, bypass it. This is the cardinality of the finite field. And that we have two G-dimensional abelian varieties over FQ like this. We order their Frobenius eigenvalues on H1. And then we look at the total, the sum of the arc lengths of the circular segment alpha I, beta I. So this is a lower bound, like a gap, which is roughly, I still don't understand what it means. Is it close to optimal, which is exponential in square root q to the power, q to the minus g, roughly q to the minus g over 2. And actually, if we look at the pigeonholing from just counting these file numbers, I think very roughly speaking, they are of the order q to the g squared over 4. And by symmetry, I think we can just pigeonhole out an upper bound, an example like this, which differs by square root from the lower bound.
So if you don't look at the interlacing, like the shadowing, I guess Robinson or Sarah recently wrote a paper showing how Robinson capacity is the answer, is optimal. Yeah.
Yeah, for capacity, so what we can say is, I will actually, this is very relevant to what I will say. Capacity is square root 2 to the 1 over 4.
Right.
This is the optimum.
That's what Sarah gets.
Yeah. And actually, this is related to why is this relevant to CM? These file numbers belong to CM fields, and this is absolutely crucial for this result. So let me begin by recalling Robinson's theorem, who transformed the circle of radius square root of q to the interval via the map to z plus z bar. Of course, on the circle, this is also rational map z plus q over z. And also on the original, even for q equals 1 and the original Schinzel-Zassenhaus setting, we can also transform the problem to the interval minus 2, 2 via this quadratic rational map z plus 1 over z. I'm not taking complex conjugate now. I want it to be a rational function. And it actually has a very useful feature, which was pointed out to me by Matt Baker. The critical, because of the critical points at plus and minus 1, if we have a point close to the points minus 1 or 1 on the circle, it gets mapped to a point which is much closer to the endpoints of the interval, just by this. So the distance was u to 1. The distance is like the square of u for after we apply the transfer map to the interval. And so actually, it turns out, I will explain, this is in addition to my paper, we do not lose anything by actually working on the interval after applying z plus 1 over z. And we can even get something stronger. We can get the analog of the sz for the interval, for the minus, for the cube of size constant over n around the interval. And this applies in particular to totally real Galois orbits of algebraic integers near minus 2, 2. But actually, we also get a stronger kind of result back on the circle. So we can even guarantee a conjugate that is outside of the union of the disk 1 plus C over n. So far that is Schinzel-Zassenhaus up to the specific C, which will be smaller here, but also adding the two larger disks of square root that radius around the points 1 and -1. And in particular, we do get this actually was a surprise to me that it has an added value over the usual Schinzel-Zassenhaus conjecture. It does not follow formally even from the Lamer conjecture. We get that a totally real analog, if we have a degree n totally real algebraic integer, not cyclotomic, not of this special form, then at least one conjugate lies outside of that segment within C over n from -2 and 2. But I want to start with a very quick review that will build up this proof with recalling the Tekete came to this quantity, the transfinite diameter, exactly by studying. His motivation was to understand Galois orbits of algebraic integers in the complex plane, and he proved that the growth rate of the Chebyshev constants of a compact set K converge to a value, and that he called the transfinite diameter. So we take the inf over all the monic degree n polynomials. There is a unique minimizer of the least deviation from 0 of the polynomial on K to the power 1 over n. And of course, I call it the capacity because we'll see in a moment, but he discovered also that it's a natural measure of size from the point of view of conformal mapping, and as found by Poya, also in an arithmetic sense. So for example, capacity zero sets are not seen by holomorphic or harmonic function. They extend automatically past capacity zero. And also Poya gave a discrete analog of this, if we have a set of capacity informally. Let me, before I get to the formal result, sets of capacity smaller than 1 are removable for analytic functions under the condition of rational integer Taylor series around the point infinity. So the limit is this limit of decreasing n diameters, and this is why it was called the transfinite diameter, the diameter for 2 points. But this is the capacity, the connection to capacities, because we take capacity for with respect to the divisor infinity on the Riemann sphere. And the reciprocal of the capacity, in the case that K is connected, is just the conformal mapping radius from infinity of the outer domain or complement of K. We have the functoriality properties under polynomials of the monic polynomials of degree R, but there is one less obvious and maybe less known property that I want to stress. I will use in a moment due to Robinson. This functoriality by polynomials is because the pullback of the divisor is just a multiple of the divisor exactly when the map is a polynomial, and that is false for rational functions. But if we have a rational function fixing infinity, and if it is of the form u over v, where again u is a monic polynomial of degree r, and the denominator is a polynomial of a smaller degree that takes the value, has absolute value 1 along the compact, then the same formula holds for inverse image by this rational function. But let me explain my phrase earlier, the scarceness of incidences for small capacity. This is based, this is why I displayed the discriminant or nth diameters definition of capacity. If we have an integer polynomial without multiple roots, then we can, in particular, its discriminant is at least 1 in magnitude. And already Fekete's formula gives the crudest restriction on algebraic integers, that the limit measures of the Galois orbits of algebraic integers, who knows what they are exactly, but they have to have supports of capacities at least 1. And I want to mention this in passing that actually Serge's paper that Peter pointed out a while ago contains an, actually it raises the question whether the Lebesgue measure of an interval can be a limit measure. Although he's in the, working in the context of totally real algebraic integers, but same question, actually the same observation works. To give a counterexample, at least the discriminant condition is this, that the sign of the energy of the measure is constant. I mean that there are two conventions that one may take for the sign. I'm taking this, then it means that the energy is non-positive. But this is not sufficient because essentially, as Serge points out in that paper, if we take the interval, this one, plus minus e to the 1.5 over 2 with its Lebesgue measure, and then the energy is 0, and it's not a limit measure since the it does not, it fails the norms constraint. The integral of log z is negative. And there is this necessary constraint on limit measures, and I just want us to convey that even on that level, it is a mystery to me what the possible limit measures are. But limit measures are not what I want to speak about. And for example, this was another problem that was raised by Serge. It seems open whether this interval with non-integer endpoints and capacity 1 should contain finitely or infinitely many algebraic integers. Discriminant constraints cannot, certainly Fekete's theorem and equidistribution theorems do not bear on this question. And I don't know yet if the method I will propose can say something of this kind of question. But the reason that one loses by just estimating discriminants by 1, just dropping them by integrality, and I will give more examples, are that discriminants should be actually large, discriminants of polynomials or monogenic orders as opposed to arbitrary number fields, and they are indeed rarely much smaller than n to the n, but we cannot prove this. For example, on the Lamer problem that I started with, the new book by Bruno and Vesselin points out, they point out that for at least for the 100 smallest known Mahler measures, it turns out that the discriminant of P exceeds n factorial. We exclude cyclotomic examples, and if a bound of these strengths were true, that would actually be enough for the Lamer conjecture, because by Matveyev's theorem, because the Dobrovolsky bound will improve enough when the discriminant is large. Otherwise, the discriminant has been dropped by just by integrality. But here is actually a more elementary observation that where we drop a discriminant. This is the root separation theorem of Mahler and Mignot. And it also, I think, grew out of Fekete's work, because this kind of result also applies for capacity 1 sets for more general heights than the Mahler measure that we have here. But anyway, the basic case is that we can pair up, again, it's like a non-shadowing result, but we don't have to include all the roots. If we take any complex polynomial of degree d and no multiple roots and any pairing of the roots, the log of the product of the reciprocals, the minus log of the product of those differences is bounded above by this quantity. And if the polynomial has integer coefficients and we drop the discriminant term, we get as a corollary, I'm stating this lemma, this is a key input in a joint paper with Philip Habegger on Galois orbits of torsion points near atorial sets, that if we have atorial means the condition that the Galois orbit of algebraic integers does not hit the unit circle, polynomials which have no roots on the unit circle. And I'm just want to point out that if we have Mahler measure bounded from above, and then this Mahler bound dropping the discriminant implies net repellency effect by 1 over n squared on the geometric mean of distances from the roots to the unit circle. In contrast, there is a beautiful paper by Robert Bruch from 1951 that I think was unfortunately ignored for more than 50 years, it seems. But he was the first to solve the Lamer conjecture in the reciprocal case. And his approach, or maybe depending on the point of view, he reduced the conjecture to its reciprocal case and used the integrality of the resultant of a polynomial and its reciprocal. So that's an integer, non-zero integer, and so at least one if the polynomial is non-reciprocal. And that is sharp, unlike for discriminants, and leads to an even stronger result than Lamer, that even the geometric mean of the distances from the roots to the circle is bounded below by a constant divided by 1. So we see the Lamer strength here, but the worst exponent if we just use the discriminant's Mahler bound. What Bruch did was to separate the resultant into a diagonal and an off-diagonal term. The diagonal term is essentially the product of distances to the unit circle because the roots come in pairs of alpha and 1 over alpha bar. And their distance is essentially the distance to the circle. But he bounded the off-diagonal part from above by that quantity. So by taking the nth root, one recovers, one gets exactly the geometric mean, and recovers Lamer in the non-reciprocal case by arithmetic mean, geometric mean. And of course, this resultant condition is often is quite sharp. I do not have time to dwell on all of these things, but there is a nice example from the Mandelbrot set that of a family of analogs of cyclotomic polynomials that give the period n centers for the hyperbolic components, these Gleason polynomials defined in this way, and they have pairwise resultants plus or minus 1, and they give more examples of incidences because the capacity of the Galois of the Mandelbrot set is 1. The points, the roots of the GN lie in the interior. They get pushed farther and farther into the boundary and towards the equilibrium measure. But now the proof of the new results are based on Hankel determinants. And let me observe that if for the Catalan and the Motzkin numbers, I'm giving their respective generating functions that are rational functions. quadratic irrational functions. All the Kronecker-Hankel determinants are equal to 1 for k equals 1, 2, and for the entire sequence of them. And now we can begin to connect the dots with the proof of the original case of the Schindler-Zassenhaus conjecture. I start with an elementary lemma that is the easiest to prove. Suppose we have just an integer monic polynomial and take its factorization in the complex plane into n roots alpha 1 through alpha n. And then I define a sequence of polynomials, also monic and integer, by raising the roots to the nth power. So, and then the key congruence for the two-adic input of the proof is this, that coefficient by coefficient, these polynomials P4 and P2 are congruent mod 4. And this is how the generalization looks for every prime. The proof is just an application of the Newton-Girard formulas for the power sums. We take the second and fourth power sums to compare coefficients of x to the n minus 1. And because E1, E2, E3, and E4 are rational integers, elementary symmetric functions of the roots, these are obviously congruent modulo 4. We can see this right away. And that's for the x to the n minus 1 terms, but in general, it follows by the same argument, just by taking the symmetric power polynomials. So it's by the same congruences by substitution, essentially. At this point, we can create a function with a power series with integer coefficients, and that its Hankel determinants are the key arithmetic input. We take the square root of the following polynomial. I take all the roots alpha of p in the complex plane and then multiply out 1 minus alpha square over x, 1 minus alpha to the 4 over x. So I've raised them to the second and fourth powers. And let's see that these, crucially, this has integer coefficients at infinity when expanded because of the mod 4 congruence. Let me write stars for the reciprocal polynomials. And then this is the mod 4 congruence, and a monicity of p translates to p star of 0 equals 1. So the free terms of those two polynomials are 1. That means that q has no constant term. And then we can just expand by the Newton binomial. So we can do the following. The square root of our function, just p2 star, p4 star, is this. I can take p2 star out by the square root, and then I'm left with a multiple of 4 times power series with integer coefficients and no constant term. So I can just expand it like this. And obviously it has integer coefficients because these numbers are integers. The apparent denominators of 2 have been cancelled, have been corrected. And so the second piece is the automatic analytic continuation of these functions. Like any holonomic function, any solution of a linear differential equation over the complex numbers, and that is very much in contrast with p-adic differential equations, has automatic analyticity up to its singularities. So if we just take a branch, so let's say this way, f of x has automatic analytic continuation to any connected and simply connected domain of the Riemann sphere that avoids the branch points. It's alpha squared and alpha to the 4 that I have used. And that is why I began with the specific form of compacts that I want to include arcs. In this case, I will take just one connected continuum to K, and it will consist of the 2n or fewer straight segments from the origin to these roots, these branch points, alpha squared or alpha to the 4. And then its complement is simply connected, and we have the desired analytic continuation. At this point comes relevant the theorem of Poya that I mentioned, and it was generalized in the Adelic setting by Bertrandias. It states that if the capacity of K is smaller than 1, then F has, well, then F is a rational function. And I will also sketch the proof, which is very short and beautiful, that illuminates the arithmetic input from Hankel determinants. These are the Hankel determinants, the matrix with starting out, just writing the coefficients of F, A1 through AK, then A2 through AK plus 1, and so forth, and consider it for OK. But we can rewrite this determinant by column operations in the following way, interpreted as a residue of this differential form, where I'm free to choose, because we apply column operations, free to choose the sequence of monic complex polynomials of degree j. Pj has degree j. We take a basis of monic polynomials. And of course, we will select the Chebyshев polynomials for this particular k that we have chosen. In fact, it is definition of the transfinite diameter. Because just by definition of the capacity, they have supremum bounded essentially by capacity to the power j around k. And now I interpret the residue by Cauchy's theorem, choosing a contour that will go tightly near the boundary k, this continuum that I called hedgehog. And then we have just the origin as the singularity because of the analyticity assumption. We just estimate the determinant by the Laplace expansion, actually, that's enough, and just placing the absolute value along the contour. That shows that all the Hankel determinants are 0, and then it's a classical result that this is equivalent to rationality. So this proves it is rational. At this point, there are several ways to continue with the Archimedean input, but the most elegant is the theorem of Dubinin from the 1980s that uses the circular symmetry of the circle that leads to the sharp best constants that the method obtains. Although I should say that the 2 to the 1 over 4 at the beginning is not strictly sharp best possible for the method. It can be slightly improved. Anyway, Dubinin's theorem is sharp, and it states that among all the continua, H consisting of n vertices of the unit circle joining the origin by straight segments, the largest transfinite diameter occurs for the rotationally symmetric configuration, precisely when the points are the vertices of a regular angle. And then we can see the transfinite diameter right away by the transformation formula, because the rotationally symmetric configuration of the roots of unity of order n is just the inverse image of the unit segment by z to the n. The capacity of a segment is a quarter of its length, and so this symmetric hedgehog has capacity 4 to the -1 over n, and that is an upper bound for the capacity of any hedgehog with n vertices on the unit circle. And of course, we can also see it more directly with Kurb's extremal function, because the Riemann map for the complement is explicit. is this. So here we see again 4 to the 1 over n for the conformal radius of the inversion of the regular hedgehog. It is actually quite non-obvious to prove, but also quite intuitive that it gives the maximum transfinite diameter. But also there are alternative ways to treat this step, and I will say more in a moment. Anyway, now by scaling, the transfinite diameter has scaling homogeneity, and also it's monotonic under inclusion. So we can restate Dubin's theorem equivalently for any points. Now using the house, so maximum of the absolute values. If we have n points in the complex plane and take the straight segments joining 0 to the points, the capacity is bounded above by this modified function. Again, we have 4 to the 1 over n in the denominator. Now we have scaled, corrected by this. And that is how the house arises. And the 4 from geometric function theory is the origin of the height gap property ultimately. Anyway, in our situation, we see that the capacity of k raised to the power 2n is bounded above by the house of alpha to the power 8n divided by 4. And the upshot is that this condition, the house of the polynomial is smaller than 2 to the 1 over 4n, the opposite of the stated bound, forces the function to be rational, and so just a polynomial. I want to mention before I move to more interesting cases of compacts, that this proof, this argument with hedgehogs applies to completely general linear differential equations, holonomic functions, or differential equations on the projective line. And if we have, for instance, the simplest case is when we have integer coefficients. So a power series with integer coefficients that satisfies a differential equation with k singularities. In that case, the height of the power series, by that I mean just the log plus of 1 over the convergence radius. And if there is a dichotomy of Carlson-Poya type, that if f is not rational, then its height is bounded below by a uniform, an absolute constant divided by the number of singular points. And what one can find in my paper is that even for rational coefficients, such a bound holds with a worse constant than this, under the appropriate definition of the height. But also, the final piece of the solution of the conjecture of Princeton-Zassenhaus is to sift out the cyclotomics. There are necessary examples, and they are accounted for by this property, that the square root of P2, P4 is a polynomial when, okay, let us figure out when that happens. Suppose first that P2 is irreducible. In that case, this can only be a polynomial if P4 and P2 share a root. And of course, that means that alpha to the 4 is conjugate to alpha squared, and taking height, we see at once that the height of alpha has to be 0, and then P must be cyclotomic. And then also n is odd because we assume P2 is irreducible. So, and in that case, indeed, they are sifted out. P2 and P4 are equal to phi n, the anticyclotomic polynomial, whenever P is the anticyclotomic polynomial. But it remains to consider that P2 may be reducible. Well, in that case, it's very easy to see that P of x is of the form just Q applied to another polynomial applied to x squared. And then the new polynomial has half the degree of P, and we just continue by induction on P. So just replacing P by Q, and that finishes the proof. And I will just say a couple of words about the total p-adic or abelian variants, that they work with p root functions instead of square roots, and just as well we could consider any prime p and take the following function. And because and the most general congruence of this of the form that we used is what Delin calls extended Euler congruences in a two-page paper. It reads like this: that for any matrix, square matrix over the ring of with vectors of length n of an FP algebra, we have the Frobenius twisted identity for traces. Trace of a to the p to the n is Frobenius, Lichter Frobenius applied to the trace of a to the p to the n minus 1. That is for the case that p is unramified, and when p is ramified, it works very similarly with the idea of Amorós and Vornicich from this paper, a lower bound on the height in abelian extensions, where they discovered the Bogomolov height gap property for the field QAB. But this is not what I want to focus on for the remainder of time. I want to explain also the theorem on Weil numbers. Let me abstract what I did. I have offered only one really new tool in this subject, and it's just we can abstract it as follows. I call this the pth root restriction, and this is how I wanted to make a follow-up on Fekete's theorem. Consider, suppose that for some prime p, an integer polynomial p of x, which has no multiple roots, that p mod p squared, the polynomial mod p squared, is a perfect pth power. And also that we have a compact that is made of finitely many analytic arcs that cover all the roots, and the covering numbers are multiples of p. By that I mean that every connected component covers a multiple of p of the roots. Then the capacity of K has to be at least 1. Because if I just do the previous to the pth root of the polynomial, the condition on to be a perfect pth power mod p squared means I have integer coefficients, and also by the congruence condition on the covering numbers, it will have a analytic continuation on the complement of the compact of K. And here is how we can use the formula for Robinson and Halist's variant of Dubin's theorem to also complement our discussion with the proof of the no shadowing property I pointed out for abelian varieties. Let's now consider, I had these Weil numbers, alpha I and beta I, that I supposed were paired in close, like shadowing one another.
Perhaps just to correct you, Weil numbers.
Oh, I never knew how. So we have Weil numbers, alpha I and beta I, and they're arranged in some way, and we assume that the total sum of the arc length of alpha I and beta I from 1 to 2g is small. So I want to actually give a lower bound on this. And this assumption is that when I take the square root function, which will look like this, the singularities will now be very near to each other. And I can actually choose compacts that will pair them up by short segments. But actually, let's pause. Why is this function, why does it have integer coefficients? I am following Robinson's idea to take the image under z plus z bar, that's twice the real part of z, and compare capacities on the circle and the interval. But it has, this function has integer coefficients this is because the complex conjugation commutes with the Galois elements. This uses a very special property of CM fields. It's essentially the definition of the CM field, and it definitely is very false for arbitrary algebraic integers. So actually, this f of x has integer coefficients. Now select K to be the union of the 2G segments here, appearing as the branch points on the real line. So I have transferred from the circle to the line. And we want to compare the capacity of this K to the capacity of the preimage E on the circle. Without loss of generality, I can assume the pairs alpha I and beta I of Bale numbers are stable under complex conjugation. So this is E will be actually the preimage of K. And for Robinson's formula that I stated a moment ago now relates the two capacities like this. The capacity of K, I had an additional scaling by 4. Sorry, let me go for a second to the previous slide to recall why I used a factor of 4. That was because I no longer use the mod 4 congruence and I want to get integer coefficients when I expand the square root. But this is fine in this case because the capacity of K is very much smaller when we go to the interval than the capacity of E on the circle. This is Robinson's relation. So it looks like this. Poya and Bertranges gives the capacity of K has to be at least 1, or the square root restriction I had on the previous slide. And that translates in terms of the capacity of the union of n singular arcs by this bound. And we see here the q to the 1/4 bound. That is the same q to the 1/4, like in Robinson's theorem or in Serre's paper. But now we can use the theorem of Haliste that was that complements Dubinin's theorem and is proved by the same method of desymmetrization. Haliste proved that if we look at n arcs on the unit circle, just take a fixed number of arcs, but keep a fixed total arc length, L, and we ask which such set has the maximum capacity. The answer is when the arcs are maximally spread out and the rotationally symmetric configuration, in which case the capacity is sine of L/4 to the 1/n. So we have an upper bound in the other direction here on the capacity of this set E. And I was just observing that if we compare the two, we can read out the result. Of course, we have to scale the unit circle to our circle, which has radius square root of q. And then the capacity of or say Haliste's bound rescales like this. This was the upper bound. I estimate this more crudely, just forget the sign function, replace it by its upper bound by the argument. And then I get an upper bound by this to the 1/2 minus 1/2 to the n, L to the 1/n, where n is equal to 2g, the degree of the number of arcs that we have. And if we compare the upper bound and the lower bounds, the point is that the lower bound is quite non-trivial. We get this resulting lower bound on total length. The Mahler-Mignot bound that I formulated before will lead to a worse estimate by a factor of 8. Again, polynomial in q to the minus g. And for the last couple of minutes, I want to appoint to some further cases where such a method applies, and they're actually not limited just to the multiplicative group. For example, I mentioned already the SZ analog around for the tube around -2, 2. And here, instead of the isogenies 2 and 4 of the multiplicative group, we can work with the second and fourth Chebyshev polynomials. Of course, they are related to the isogenies by the covering map, but they by themselves satisfy the necessary mod 4 congruence, and we can work directly with real segments rather than pulling back to the circle. That has certain advantages, but even beyond, even for cases that are not related to the multiplicative group at all, we can now get Diophantine repellency properties of Julia sets of certain quadratic iterations. If we take z squared plus c for any integer parameter c, let me illustrate by the most interesting of these. Z squared minus 1, for which the Julia set is neither a circle or an interval or a counter set. Then the key congruence works as follows. We take the first and the third iterates, and mod 4, they are congruent. The third iterate is congruent to q of x to the 4 mod 4. And that will work for the square root lever, like in our previous argument. And just as we sifted out cyclotomic polynomials, pre-periodic points as the necessary examples are also cleanly sifted out by an exact dichotomy, to be either purely periodic or strictly pre-periodic. These are the cases where our auxiliary square root function would be a polynomial. So I see that I have to end with this slide. So I will, this will be my last example. This dynamical setting will be a joint project with Matt Baker and Philip Habegger after the very interesting observation with the interval -2, 2. But at least at the moment, I can give a new Bogomolov property using this idea. For the quadratic iterations, for instance, z squared plus c, and c, where c is any integer, rational integer. Let's take this example. The dynamical height function has the strong Bogomolov height dot property on the Abelian points. Basically, the QAB argument works exactly in the same way. And in particular, if we take the case of cyclotomic numbers that are the values of fixed Laurent polynomial at the given at the varying root of unity, we get that non-constant images of integer Laurent polynomials evaluated on the circle must stray at least some fixed amount away from this Julia set, which has capacity equal to 1. Thank you for your attention, and I must conclude at this point.
Thank you very much. Are there any questions?
I guess I have a few. Question 1, if instead of looking at abelian varieties, you looked at Jacobians over a finite field, then as Vladut and Fassmann proved some years ago, so what you were showing there was this shadowing, but before the shadowing, you could ask if you look at these Weil numbers, what's the smallest set they could concentrate on abelian varieties of bigger and bigger dimension. And what Sarah's saying is basically this capacity constraint is the only one. But for curves, they're much more restricted, and Vaj numbers have to become dense as the genus goes to infinity. And that's because you input some other inequalities coming from the fact that you're the Jacobian of a curve. My question is, maybe there's some shadowing theorem that for curve that's much stronger than your theorem. Can you exploit that?
I would love to. It sounds very interesting, but I would also expect it probably should improve.
Because they're already, and there's a basic, very interesting unsolved problem similar to this as to what the limit measures can be. They have to be supported on the whole circle if you're coming from curves. And even for these Jacobians, that's why Sarah was saying that while you know the capacity of the set, you don't know the limiting measures. That seems hard to classify. As you go through abelian varieties of higher and higher dimension over a fixed FQ. The other question I had was in this last theorem, where you're looking at the Julia set, or I don't know what the Fatou set, the Julia set there, I get mixed up between them. So suppose I have a rational map. You said, suppose that the set which doesn't go off to infinity under iterates,
Yes.
Is real and is a Cantor set.
Yes, that includes cases. Yes.
Yeah, then the capacity, I think, is decisive. You say you have an improved bound, or is this some theorem about shadowing again?
So firstly, so this example I wrote, z squared minus 1 is not an example of Cantor set. But yeah, but if you take z squared minus
5.
6, or 5, yeah, or 5. Yeah, that works too. Yeah, so it's a Cantor set on the real line, right?
Yeah, so it's a Cantor set on the real line, and the capacity is 1.
Yes, right.
And what are you saying? What new are you saying?
Firstly, the dynamical height function, that is the global escape rate, this growth of the height along iterates, has the Bogomolov property on QAB points. That is
so on abelian points.
Yeah, it can be KAB as well for any number field, but okay. But actually, this is an ongoing project. It's not finished, but I think for that case, when the Julia set is Cantor set, we should be able to get Schinzel-Zassenhaus bound as well. So this would look like we expect that the tube. How do I write? If this is a Julia set and I consider it C over n thickening.
The Julia set is this Cantor set? What is it?
Yeah, the Julia set is this Cantor set. And I consider a neighborhood of with C over n for some.
I see a quantitative. Yeah. Okay.
Yes. Then essentially we asked for. So Robinson's theorem was that if you take any subset of the real line with capacity strictly bigger than 1, you can find Galois orbits of algebraic integers. But we want to find this, to refine this quantitatively in the spirit of Schinzel and Zassenhaus. And we suspect that if we take C over n neighborhood for a given n, that should not contain, once C is small enough, it should not contain any Galois orbits of algebraic numbers, integers, that are not just among the pre-periodic points.
Right, I understand.
But I don't know about, maybe no shadowing, similar kinds of statements can be also considered in this case.
Right,
by the way, if I put, yes.
Yeah, no, that's different.
Yeah, but it's still a Cantor set, right? So it's not contained in the real line, but
yeah.
I think this one is the most interesting. It has Hausdorff capacities strictly between 1 and 2. Mm-hmm. Yeah. But it's quite limited. We can also consider certain non-quadratic iterations, like z cubed minus 1 will also work with the prime p equals 3. That was cube roots, because it turns out now that the fourth iterate of this map has the right congruence property, but it's just congruent to z to the 81 minus 1 mod 9. And it's quite,
Yeah, that gains you a lot. I agree.
yeah. But it's also quite limited. For example, I have no idea what to do if I have z² plus c, and c is not a true integer. Say this.
Yeah. Of course, if you're not monic, then the capacity formula, if your formula, what you call functoriality on the Robin constant, what I call the Robin constant, if your coefficient, your leading coefficients are 1, then the formula is not just the root, it's got the coefficient in it.
Oh, yes. No, these are R1, but the parameter can be, yeah. Actually, because I ended with the Bogomolov property on abelian points, I think I should mention that there is a very different result by Nicole Looper, which also gives Q-up points, Q-up Bogomolov property, but for completely different iterations. And her condition is that this works for the case of polynomials, which have super attracting periodic point, and also at least one prime of bad reduction. So I can put it like saying that there exists a non-trivial p-adic Julia set. So somehow it's completely different from these examples I give. But we hope to get more than just Q-up points, to get even relative results over Q-up, for example, like involving the degree of alpha. Just don't know how much the method can be pushed towards the cases of the dynamical Lamer problem.
Yeah. Are there any further questions?
Could I ask a couple of questions?
Sure, yes.
Okay, so let's see. So first, the statement you made about Weil polynomials, or varieties. So suppose I'm interested in some situation where I'm not considering algebraic integers exactly, but I'm considering algebraic numbers where I allow some very limited denominator. So like a typical example that's very interesting from K3 surfaces is I have an integer, a reciprocal integer polynomial with roots on the unit circle, but the constant coefficient and the leading coefficient are not 1, they are maybe 2 or some other prime. So can one carry a lot of these ideas over to that kind of situation?
Do all the roots lie on the unit circle?
Yeah, all the roots lie in the unit circle.
So they are of the form alpha bar over alpha, and alpha is an integer in the CM field?
Yeah.
Okay, yeah.
Yeah, it's just that I'm allowing some denominators with some very restricted, right, I'm allowing the Newton polygon to be something slightly at 1 prime, say.
I see, yeah.
That's a special denominators.
But then all the roots will be on a circle of a radius, the square root of an integer, right?
Yeah.
But the integer is not necessarily a power of a prime. So that is what you have.
Well, in this case, it would be, I mean, yeah. I mean, I'm like, if you start with a K3 surface, you start with the situation where the roots are all on the, say, over FP, then you start with everything, the absolute value of Z is equal to P. But you also have this information about the Newton polygon at the prime P that you want to factor in. So I was wondering whether that kind of information can be accommodated in the method.
Actually, firstly, I should stress that the same result I sketched applies to any Q, to any denominator. They do not have to be, finite fields and Weyl numbers, numbers, but that's quite interesting. I need to think.
Does this come up in your algorithm to sort of understand these Weyl numbers by moments?
Yeah, it comes up especially when you're not interested in abelian varieties, but in higher dimensional things of weight greater than 1. Like, for example, K3 surfaces, middle cohomology is weight 2. And so you're in some situation where, of course, you could just forget all the information other than it's a Weyl polynomial, but you have this extra information of the Newton polygon coming from the comparison with the Hodge polygon. And this is information that really cuts down the search space quite a lot. So you would like to know whether there are, whether you can combine that with Archimedean information in this way.
Right. Yeah, you once discussed this, right? Yeah,
we can maybe. I should take this offline. But I had two other questions that are in different directions. One is when you mentioned at the end you were talking about Bogomolov gaps for the torus. Do you expect any of this story to have an analog for, say, Bogomolov gaps for elliptic curves or other abelian varieties?
So far, say elliptic curves, because so far the method was considered in one dimension.
So let's just say elliptic curve.
Right. So that would mean to have lattice maps, if you like, for the canonical heights, and it might be. But so far, I have looked at polynomial maps because they lead to congruences, and they have bounded compact Julia sets, unlike.
So you would need a rational function. A generalization, which maybe is
but
more.
Wait, if you look at QAB height gap properties, this is known for abelian varieties by theorem of Silverman and Matt Baker. So and even more, there is the theorem of Habegger that if you take any elliptic curve and you can look at its division points, and then points rational over that field, and then the canonical height will have the Bogomolov property on this field, which is larger than the QAB.
Yeah, I guess, are those results effective, right? Because your methods look to be quite effective.
Yeah. They are actually everything. I think all results of this spirit for abelian for QAB are effective.
Okay.
And certainly the ones I sketch. You had one other question, but I just want to insert one remark about the CM no shadowing property also extends to Galois orbits of CM points that are near the circle, not necessarily lying on it. But some condition like CN is crucial. Of course, they are completely false for algebraic integers.
Okay, right. So maybe I can ask my last question.
Yes.
Can you put the slides back up?
Yes. Should I share again? All right. So let's see.
So I wanted to ask. You had a slide where you mentioned a statement about a differential equation with and a solution over the integers. You can go back to that part.
Yes. This was right here. No. Yeah.
Here. No, there was. This one.
Here? Yes.
Yes. So was this a special case of some more general statement about I don't know what level of generality we're talking about? Functions or something more restricted?
Oh, sorry. More general.
What is sort of the sort of scope of the more general version of this statement?
We can consider a function with rational coefficient.
Maybe you can unshare the screen now to make.
Sorry. Then you will see my blackboard. Okay. So
I just wanted to
sharing.
Yeah. Okay. Now you can switch. Yeah. That's good.
Now,
Thank you.
all right. So it's very rare to have integer coefficients for holonomic functions. That's
Exactly.
kind of upper these miracles, and yeah, but you always have rational coefficients. And there is a natural notion of the height that we can still define in this case, and that is basically the height in the definition of G functions. But let me define. So I take the upper exponential growth rate of the logarithmic heights of the polynomial of the truncations of the power series. So yeah, I take the coefficient up to the end, so the power series expands like this, an x to the n. And this is its height. So for instance, the height of the logarithm series is 1. So this is logarithmic absolute file height. And then the theorem states there is a dichotomy in the style of Carlson. That so suppose that f is holonomic and satisfies the linear differential equation with a total number of k of singularities. So let k be the number of singular points. Just of the differential equation, and then either f is rational and indeed of the very special form, just a polynomial divided by a product of cyclotomics or something like this. Oh, I should something like this. Or this height is bounded below by an absolute constant divided by the number of singular points.
Okay.
That is actually a generalization of the Schinzel-Sassenhaus problem because it occurs when f is 1 over a polynomial. Yeah. Because then this height is just the log of the spectral radius of the polynomial.
Yes, great. All right. I think that, yeah, thank you.
Thanks a lot. And I would be very interested to discuss in person about file numbers. Yeah.
Maybe someday we can travel.
Yeah.
And I believe we have one more question from Sikander.
Hi, thank you. I was wondering if, so I was trying to understand your pth root construction in terms of geometry of hyperelliptic curves. If you can go to that slide, please, that would be.
Yes, let me share again. Share. Sorry again.
So the pth root construction, you started off with the polynomial and then you had this set of k analytic arcs.
This was here.
Yes.
Right.
Right. So you can consider the hyperelliptic curve branched over the roots of the polynomial px.
So I start with a polynomial and I consider y squared equals p of x.
Yeah. And then these finitely many analytic arcs, if they begin and end at the branch points, they would live to homology classes of the elliptic curve.
So I pair, P should have even degree and pair of the roots.
Right, yes. Yes, this way. So these arcs would live to closed loops upstairs and they would actually give a, well, are there 2G of them? Would they give a basis of the homology?
I'm not,
you need to, yeah.
Do you want to look at?
The ones that you have drawn will live to closed cycles upstairs and they will be elements of the first homology. And can one define capacity of these arcs in terms of the geometry of the hyperelliptic curve?
All I did was so far a discussion on P1. So you want to look at other algebraic curves first, to not.
Yeah, so branched cover of P1 and precisely over these roots.
Okay, first off, I should say that the Poyar-Mercandius theorem does generalize, and this is a theorem of This was done by Antoine Chamberlois and Jean-Benoit Bost. Bost and Chamberlois. But I don't see how, if you do it on, if you consider the function square root p on this hyperelliptic curve, then it's rational.
Mm-hmm.
So you're not doing, all the juice came from considering an irrational algebraic function or holonomic function on P1 and getting some constraints from the rationality criterion. So if you want to do this here, you should work with an irrational function on C. Yeah, certainly capacity theory works well on algebraic curves, and the arithmetic rationality or algebraicity or holonomicity criteria generalize to any curve.
Okay, thanks. So you're saying one has to look for irrational functions on these curves too?
Yeah, at irrational functions. Try to apply maybe Bost and Chamberlois theorem.
I see.
But but one can always just take the covering on the projective line. So if one uses C, one has to find good ways to exploit somehow more analyticity. It's not clear how you can use C to your advantage, something that you can't get already.
Well, the only advantage I was seeing was that these arcs lift to give homology classes. But
in any case, you need a irrational function.
okay. And just a small clarification. So in the previous conversation, so you're allowed to have differential equations with irregular singularities?
Oh yes, there is absolutely no constraints on the singularity. And you don't care about multiplicities neither. So K was just the total number of singular points.
That much.
And that's all. It's completely uniform. But the bound is trivial if f was not a G function actually. So if the height was not finite, then of course this is pointless. So actually the singularities are regular. Yeah, this is only interesting for G functions.
Thank you.
And the last thing I wanted to say, now that we are here, I mentioned this bound. The height of a holonomic power series is bounded uniformly by 1 over k. I would like to know if the tau invariant for the power series satisfies a similar bound. And this is a common quantity in the Grothendieck-Katz conjecture that one takes the inf of the depleted height of the power series. So the same definition, but we remove finitely many of the places of the primes from the height. And that is the truly global part, the part of the height that comes truly from denominators and not from convergence area informally. So in other words, there is a decomposition that the global height is the sum of log plus of convergence radii, and then plus this remaining quantity tau of f. And very little is known about it. And so I'm asking if tau of f is not 0. So if it's strictly positive, does it also satisfy such a height gap? Is it bounded below by a constant divided by the number of singular points? Again, essentially.
Okay, then let's officially end the seminar and thank the speaker again.